Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very pleased today to have Eva Thodoris visiting us. She's a professor at Cornell University and was a leader in algorithmic game theory. Does a lot of wonderful work on smoothness and understanding the welfare of various auction designs. She won the Gödel Prize in 2012. For one of her papers on selfish routing, which was hugely influential, and the Fulkerson Prize in 1988. So thanks, and
thank you. So thank you. So I guess this talk is about games in general, and I'm going to somehow alternate between a sort of more game-oriented thing versus a more auction-oriented thing. Whichever, for each of you, whichever you prefer is fine. What I'm more focusing on, or what I'm definitely focusing on, is this dynamic population at the end of the slide. That is, it's a game that's going to get played repeatedly by a bunch of people, and dynamic meaning that bunch of who exactly is around is going to be changing, like it's not steady. That's sort of the main focus. So anything that you do that is a repeated interaction between things or people where those things and people are not completely stable, that's the application you should think of. One application, and that's sort of the more game-oriented application, is traffic routing of any form. And I guess these two pictures are supposed to make you think of cars as the form of traffic and packet as the form of traffic. That's definitely one of those situations. If you're a router, or if you think about a router is sending packets. It's doing this over and over time. The packet destination, origin, destination things change. In the mornings, different in the evenings. Today, it's a little different than yesterday. That's definitely something that repeats over and over. And the population, which in this case, the sort of packet origin destination pairs, are not completely steady. They're also not completely worst case. It's not like, a minute from now, it's completely different than it was right now, but something of that form. So we're going to think of my main focus, and that has been maybe the main focus of almost everything I've done in this game theory area, is what usually have been dubbed as the price of energy. That is the quality of solution due to selfish behavior of players. Actually going a step further, because this is going to be a sort of dynamic setup, both the selfish behavior of the player and the learning loss. That since the population is changing and they're going to have to adjust to this changing situation, they're going to run a learning algorithm. I'm going to assume they're running some sort of learning algorithm. So loss will come in two flavors. One, they not do such a good job learning, and second, they trying to learn to selfishly optimize for themselves, and that comes with a loss. And these are the two losses that we're combining here. It's a repeated game setting that we're assuming that the same game with slightly different population or players is played over and over again. And again, you can think of traffic routing, which is one application. But if you prefer, auctions, especially ad auctions, are a great example of a similar not this kind of auction, but ad auctions, are a different similar situation where the advertisers are over and over trying to buy ad space. Like they want it tomorrow and day after, or every 10 minutes or every 10 seconds. They repeatedly would like to buy. And here, it might be the players that are somewhat changing. There are other aspects of the environment that are maybe more honestly changing than the player population. But things are a little bit changing underneath them as they move. So what do I mean by price of energy? So if I go back to the last 15 years in game theory and thinking about games and outcome of games and social welfare, this price of energy has been an important concept. And what we're trying to say is compare, what we used to try to say, is to compare the Nash equilibrium, that is the stable outcome of a game, compared to a socially optimal design that may be selfishly not sustainable. One theorem of this form with Tim Roughgarden is in traffic routing that says that in concrete, this version of the theorem says that if you compare the traffic of a socially designed solution in which I tell every piece of traffic which way to go versus one that people choose the shortest path by themselves, then the socially optimum can unfortunately compare quite badly. That is, the Nash could be a lot worse. But if I give the social optimum double the traffic rate, which is what's written here, then apparently it's at least as, Nash is at least as good as the social optimum with double traffic rate, which would say that if you designed your network to withstand double traffic rate, you're OK. More generally, this is what price of energy was. So cost of the some Nash equilibrium compare against the social optimal solution. And you should think of this as cost of the worst Nash equilibrium, that I don't want to be predictive of which Nash equilibrium people will choose. As long as they chose a Nash equilibrium, the cost is, and this price of energy is not too bad, then the cost is not too bad. OK, so this is the basic setup. And question? Oh, yeah, definitely. So one form of refinement that's fair to ask, I can limit myself to pure strategy Nash equilibria, and that might be better than mixed strategy Nash equilibria.
Stable.
Could be stable. That's another thing. Yes, yes. You can try to improve this by selecting the right Nash equilibrium. I wasn't going down that path because just about a second from now, I'm going to try to make it worse, not better. So. OK, but as I told you, oh, yeah, this is the traffic routing. There's also a lot of auction-based kind of games. And I forgot about those lines. Anyway, forgot those lines. That's a mistake. It's a bunch of auctions that you can analyze this way. Unlike the sort of classical auction design, which is truthful, trying to get people to reveal the valuation, here the principle is that you're running something quick and dirty and hope that things work out OK. And I put, like, you can selling multiple things. You can sell them at simultaneous first price auction, simultaneous second price auction, generalized second price for the ad auctions. And actually, maybe one paper of ours that I like is you can mix different kind of auctions. You can buy some items on first price and some on second price, or some on a hybrid auction, and you can try to prove things about them. None of these are truthful because there are all kinds of issues between the multiple items, but you can analyze it with the price of energy kind of setup. And there are lots and lots of papers by many people, some in the audience and some not in the audience. And I maybe should point out Vasilis Syrgkanis as an author in many of them, who is one of the lead contributors here and a co-author on what I'm presenting. And hopefully, you guys all think highly of him as one of your colleagues here, or almost here. OK, but I'm going to think about repeated games and repeated game setup, which is why I'm not going in the, that's the extension direction I'm going. So I'm going to think of a setup where we repeatedly play the same game. And this is a simple chart to tell you what I mean by a repeated game. So again, think of traffic routing, think of auction, or think of an abstract game if you want. So this is minute number 1, where there are n players, and they each shows a strategy. The upper index is the minute, or the day. Step number 1, it shows a strategy, and something happened. And then same thing happened the second day, and something chose a strategy, something happened. Every day they chose a strategy, something happened. I'm going to assume that they're going the exact same game, or might be coding some variation on game, but the simple way to think about it, they're playing the exact game every single period. And the players have additive values over periods. So for example, if you're doing traffic routing, if you're sending packets over and over again on time, you care about the average delay. That would be you care about the sum. Or if there's some cost, you're adding up the cost. Or in the auction setup, you want as many impressions as you can possibly get with additive valuations. So that's the two basic assumptions. You're playing the same game, the same setup. This additive value is important, as in what you've won previously doesn't change your desires tomorrow. You still want another item. So that's what's happening. And I guess what I'm trying to model with learning is that here, when you start, you really are rather clueless and you don't know what's going on. But over there, many, many steps later, hopefully you got smarter. Like you somehow see what the other people are doing and react to it in some way. Now, what could I model as reacting to it? And something that's not on my slide, and I could do it, but it would be very, very complicated. I can think of this whole thing over the whole time horizon as a single game with very complicated strategies, and try to analyze it. And that's classically has been believed to be very, very complicated and hard to think about exactly what might be right thing to do, or even worse, there is the Folk's theorem that every idiotic thing is a Nash equilibrium here. So Nash equilibrium is not going to be a powerful enough concept. Here's another thing I can do. I can think of the classical one-shot game Nash equilibrium as my solution concept. So what would that mean is I believe that somehow, whichever way, these players will figure out how to play something stable. So they do something up front, they don't know what to do, but when they know what to do, they settle into a Nash equilibrium. And I mean now the Nash equilibrium of the single-shot game. So what that means is that they repeatedly play the same strategies over and over again, and what's better, they're happy with it. And they're happy with it, this is the notation I'm going to use, and I have a dual version whether you're gaining something or losing something. In a cost version, it says that they're playing the strategy vector S, and this is the cost of player I in the strategy vector, and the cost when they play that special strategy vector that's Nash is no better, is less than or equal to any other cost they had they deviated to some other strategy, or similarly matchingly utility backwards. That is, utility is bigger than utility for any other strategy. Yeah. Yes.
One is that I wouldn't use the word repeated game if this is what you're going to go to, because it primes in the in the minds of any economist that you're going to be talking about the relationship across things.
Yeah.
Usually for this setting, people describe it as learning in games or evolutionary games or something like this, explicitly to like prime the audience not to think about the links across different stages. And the second thing is, I think in this context, because you're usually thinking about very large populations, one very good way to justify this sort of thing that you're doing is to say that nobody believes they have much of an influence on the aggregate state that people are then going to react to. And so it's sort of reasonable to think about these more one-shot notions rather than thinking about the long-term evolution of the... Isn't that the...
Okay, so it's a great point, and I certainly have an issue with what you warned me I will have an issue with, priming the audience to think about across steps, and maybe I should use better words. But what I really intend to do is go halfway between the two. That I don't like this because it's very stable, and there's this magic of how they found the Nash. And I don't like the other one because that's very complicated. And what I'm proposing is a halfway solution between the two.
But I think the halfway solution you're going to do is going to be something that we would call evolutionary games. Or
it's more,
games, which is, there's just like a whole literature on that.
Yes,
when you
there
say
is.
repeated games, people think about it in one category.
Okay, I'm happy to take your advice to avoid the word repeated games. For those who maybe want to still see what I mean by learning in games. So I don't like the stability assumption because it assumed that they're reaching a stable outcome. For those who are more primed in the computer science literature, computing that thing might be computationally hard. So that might not be very rational. They can't do it because it's computationally hard to get to that. But here is something we could do instead that's very similar to this condition without erasing all that green up there. And here is what that looks like. So they're doing something which is not going to repeat and not going to be stable. But instead, it has this Nash equilibrium property, which I'm going to call the no regret property. That is, if I compare what the cost they got, and now this is sum of costs over all the time, compared to a single strategy with hindsight, they should do at least as well. That would be a really no regret. So that says if there is a super good strategy X, a stable strategy, please wake up to it and do it. Now, maybe this could easily be a strict inequality. It could be strict for every single X. It could be that somehow this player is really good at this and does X when X is a good thing to do and does Y when Y was a good thing to do. But if there is a stable X that's good, please do at least as well. Now, I didn't actually really mean this because there's the learning error in the beginning. So there's a little learning error in this. So what I really mean, I'm going to say that regret over time t is the sum of the cost that the guy achieved compared to the fixed strategy with hindsight X. And I want to assume that this regret error goes to 0 or doesn't grow as fast as time t, or regret over time goes to 0. And in particular, I want it to be little law of t, that is go less fast than t. They're very, very simple and natural algorithms. Indeed, a light literature of them that basically grow at the rate of root t. Yeah.
Not know? Do they know the outcomes of the games? Do they know what are they trying to
Yes, that's a gate point, and in fact, it should have been on my slide. It's not. In order to get this learning rate, I'm assuming they get feedback about what would have happened had they done all the other strategies. So for example, if they know what everyone else is playing, then that's full feedback, and then they can learn at this rate. You can achieve the little law of t rate even if you have to do an explore-exploit trade-off. That is, you have to try other things to learn what would happen in these other strategies. So there are two things on the slide. One is just says regret, which I can define independent of the feedback. And then I like algorithms that have little OT feedback. And then I make a concrete claim of how small I can push that down, how small I can make the regret get. That second statement depends on having full information. If you have to explore and try to figure out what these other strategies are that will hurt you, and it still will be a little of T regret, but not quite as small as what I'm giving you. Okay, so
clarifying, so
yeah.
The costs are a priori not known, and they're learning it as they play the game, is it?
Exactly.
Okay.
No, is it the cost or the strategies?
No, so the assumption is the strategies they know. The game definition told you what the strategies are. Like you know the network. You know which way you can drive. You know you have a map. What you don't know is where the bad traffic is. And there are two options. Up to here, it doesn't matter which option you're in. One option, I mean, ignoring the last part. One option is that you only experience the things you drive someplace, you know how long it took. Or you bid on something, you either won or you didn't. You know how much you paid. And you know whether you won or not. But you don't give you feedback of the form of what happened in the other routes that you didn't try. What's easier mathematically if I give you full feedback. That is, I tell you that, well, you didn't win because your bid was 7, the winning bid is 8, and someone else bid that. Or it's a radio who announces how bad the traffic jams were everywhere. With full feedback, that is, you know how bad, what you would have gotten had you went someplace else or did some other strategy, you can push the regret down to root t.
Do I need to know what the cost functions of the other people
No.
are?
No, just your own.
But so I'm actually, and do I learn the cost functions or do I actually only learn the strategy?
You only need to know, you know up front your strategy space, you know what, you don't, it doesn't matter what.
But which one I want to play, I don't know.
Correct.
I don't know whether I
Correct.
want to drive via Cambridge or
Yeah.
via.
And there's no
I
assumption.
learn what to play. That's why it's called learn.
Exactly. And you get feedback of your cost. You don't know the cost function. You don't have to necessarily know how the cost function depends on anything.
Not even my own.
You just experience the cost. In a full feedback version, and you also get feedback of what your cost would have been had you done something else. In the limited feedback version, you have to experiment to figure that out. Question?
So for this, you just get feedback on how a different strategy would have changed an individual time step, not how that might affect other time steps?
Correct. So again, the assumption is, and it's a great questions, and maybe stop me without any other sort of clarifying questions because these are important. What's the feedback structure here? If I want the best algorithm, the simplest algorithm, both simplest and the best performance for learning, then what's in the bottom here, that is that grows only with square root of the time, then I'm assuming full feedback, by which I mean not only do you know what happened to you, but you also know what would have happened to you had you done something else. So in the rating context, the assumption is you drove, it took 7 minutes, but you also listened to the radio and you heard that the Massachusetts Turnpike is really congested. People are standing there for 2 hours. So you know how long it would have taken had you gone on the Massachusetts Turnpike. That's the full feedback. There is no assumption in place, and this will actually be important, that you know what the opponent's experiencing. You don't know that the what action of the opponent causes you to have this sort of pain in your life. In fact, the learning results are not only applicable in games, but applicable in a much broader context, where you have some set of actions that you can choose between, which we can call strategies, and you get some arbitrary worst-case feedback of which strategy is costing how much at every time step, which can vary by time steps, which we know why, because your opponent might be doing something else. Yeah.
Okay, so 2 questions. So one is, I guess by strategy you mean what I would have thought of as an action, right?
Yeah.
Think of strategy
Yeah.
being, right, okay.
Oh, I see.
Right, because it would be conditional the information sets. Okay. But then the second thing is there a reason to believe I guess you're saying I have algorithms that guarantee I have no regret I imagine, I'm in this environment where people keep doing different things. Maybe it would be really hard for me to do well against an environment if there was something adversarial about the way people were playing going into the future. What am I struggling with here? I'm learning from my outcomes. People are doing different things. If people are behaving maybe in I don't know what this regret is about exactly. I know that I should be able to look backwards and not do that badly, but does that tell me anything about going forwards or?
So it's a great questions, and I don't know whether this is maybe let me respond to it because you asked, even though I was planning to think about it a little bit later. So I guess one important fact here is they're very simple and very natural algorithms that guarantee this no regret. In fact, if you're running an algorithmic tool to adjust your bidding, it's definitely hard to avoid doing well. The one important, or doing well enough for this. The one important thing that you have to do that's sort of one way to fail, one classical way to fail, is that the algorithm has to have some randomness in it. So in a worst case setup, because I made no assumptions of, these algorithms don't make assumptions that the other guys are learning. They can do actually especially screw you. That's their plan. So if you're running a worst case a deterministic algorithm and the other guys really want to screw you, then they can do whatever route you choose, they all choose it too. And then you guys are all on top of each other. And that happens all the time. So in order to achieve the no regret, you have to randomize so that this kind of opposition doesn't work. But very natural, very simple algorithms achieve it. One. But I also, as something I mentioned you when we talked earlier, this is not the paper I'm talking about, but it's a great question of whether people actually do this. So I'm not going to make the assumption that anyone's using this algorithm or that algorithm or any of the or a fictitious play or any algorithm that all achieve this. I'm not making that assumption. I'm making the assumption that they achieve this, whichever method. I don't care whether one of these on the list or not on the list. So one's supposed to look at data and figure out, do they achieve this? And I guess for a concrete data, I don't know what the proper time here is, but how much regret error is there? And we have been looking with Vasilis and Denis Nekepelov at Microsoft data, actually. And there are very interesting facts in the data. We have an EC paper explaining our current progress and many more questions that we're trying to address that we haven't addressed. But we do know right now for that particular, so Microsoft data looked at ad actions. It's an older data set where ads were more simplistic. So you didn't have to worry about the fatness or size of the ad. It was one slot, one ad, which makes life easier. And we looked at only ad bidders who frequently change their bids. That made us think that those guys are using some sort of algorithmic adjustment tool, because otherwise humans don't change that frequently. So they must be algorithmic. On the plus side, a good fraction of them, 60-somewhat%, have no regret. Interestingly, some of them have negative regret. That's a form of no regret. I told you, you can do better than this. No one tells you to use a fixed bid. I'm only comparing you with a fixed bid. It's physically possible to get negative regret, and some of them do have negative regret. That is, they do better with any fixed bid with hindsight. But about 30 to 40%, I forgot the number, actually do have positive regret, and quite high compared to their value. Some random number between, like, essentially uniformly distributed between 30-40% of their value. So there's a large fraction in the data we're looking at that have that. But I don't know actually. So this is where we are currently, and it would be interesting. Are they trying to be clever? Yes. Or no, I don't know the answer. Yeah. So what I really want to know is.
Well, all of the ones she looked at.
We only looking at.
So were they trying to be smart? Were they just frustrated at being random? But you don't.
So one thing I would love to know is whether, if you look at the sequence of these events, the people or the listings that have high regret value, what happens to the, how do they change their bid, and do they go towards the thing I think they ought to be regretting? I have an idea what they should have done. Are they going towards that thing? A, and B, does their regret go down? So are they doing actually?
Following them long enough, you don't have a data set which is following them long enough to see if they eventually learn.
Yes, so we have some correlation of how your current regret value corresponds to the amount you're shading your bid in our estimation of your value, which of course is also questionable. This is an ongoing project. We put the current version in an EC paper, and which is up on all of our web pages and at the EC web page. But there are still many questions here. I think it's in line with people are learning. It's also in line that the standard might be hard for some people because some listings do have regret. There's also the issue of, do we have the objective function right that they're optimizing? We're assuming that they're optimizing number of clicks times some number of value, and some people might be optimizing something else. But it's a good question.
Trying to get impressions or something, they
Yeah.
might be optimizing.
Yeah, they might be optimizing a different objective function. One thing to notice here, and it's in part why I put in the fixed strategy Nash equilibrium into this presentation, is that this assumption is weaker than the steady Nash equilibrium assumption. Like Nash equilibrium, if I went back to the version with all the green on it, that of course has no regret. One particular way to reach no regret is that to find the Nash equilibrium, but there are other ways algorithmically more reachable that are reaching the no regret. Yeah.
Where like the stability thing comes back to me, because even though I agree with what you just said, any reasonable process of learning will only reach stable equilibria. They won't reach unstable equilibria. So there are some Nash equilibria which any reasonable learning dynamic will rule out, and yet which isn't ruled out by exactly the definition you just gave.
Excellent point. So I guess the definition I gave, and this is why I said I'm going in the other direction from finding particular equilibria. Actually, so okay, the point you're making is that there are some stable equilibria that there are dynamics that might find it, and then there are unstable equilibria. There is no, when I said that decent dynamic has to randomize, or any hopeful dynamic must randomize, and no randomized equilibria can settle on them because they're unstable. So this learning will never find those. On the positive side,
Or anything nearby it either. I mean,
good point. Yeah.
They're repulsor points.
Yeah. Excellent point. On the other hand, there are dynamics that this thing can go to that are not equilibria. So there's no guarantee that even if I said this guarantee is about the single player loan. I can guarantee no regret for myself, independent of what the rest of you are doing. This, by the way, a very attractive property of learning, because just in case the opponent's playing stupidly, I shouldn't play Nash. I should take advantage of the mistake the other guys are making. And learning does that for you, helps you take advantage of them. But even if everyone does no regret learning, and even if I take the order T error at and take the limit as time goes to infinity, what they converge to is what's usually called correlated equilibrium, or putting it the other way, they don't necessarily converge to anything stable, but they might sort of cycle around. Like for a while I'm winning, and then Christian wakes up to the fact that I'm doing something and beats me, and then I wake up to the fact that, oh, Christian's doing that, I guess I should change my strategy, and we can cycle around forever and ever, never ever settling on anything. Yet, on average, we have no regret. So we're not doing anything stable.
Now, if we are talking about money, then I'm losing the square root of. So if I place a stock market like that, I'm guaranteed to only lose square root in time, but I can lose a lot, because if time goes on, I lose more and more of my return.
Well,
square root of t.
So I guess this, assuming things are somehow normalized, to say the maximum cost or maximum utility is 1, you're making some amount of utility. I think a better measure is the amount on average, like on average, how much cost you're losing.
Relative to Jim Simons, you're still making some money. You're just
every day you're making $1. On T days you made $T, and relative to that you lost root T. Yeah. But relative to what you made, you're losing less and less. Right. I mean, the relative error goes to 0. Remember, the value is additive. They're T time steps.
If on average, whatever, the Microsoft stock over the last 30 years earned 1% per day, then
Then T days is T%. Of that, I lost root T. Yeah. So it's an off, like little off compared to what you're winning. Okay. So that's, yeah, okay. In a beautiful paper, or pair of papers really, of Avrum Blum and co-authors, including Katrina Liggett and Aaron Ross, they introduced this phrase called the total price of energy, which is trying to lift the price of energy to learning outcomes. So now I took away the stability. I want to know how bad are learning outcomes. And I guess going back the framework I'm actually also going to use is this smoothness that Nicole mentioned in her introduction, is analyzing price of energy via a particular technique that has the beautiful advantage that it works on learning outcomes. It doesn't have to go to Nash. And here is what it does, and this is the schematic picture of what these people suggested. So price of energy bands for Nash equilibrium. So this is this repeated game. I now be very clear reminding you that it's the same population playing at every single time step. And they claim that for most of the price of energy, or almost all the price of energy bands we knew, it has the nice property that in this setup, when you repeat the players over and over every time step, then even if they're just learning, it may never converge to Nash, but the same price of energy bands work. I really, really like this piece of work, and as Nicole pointed out, I have been working on consequences or applications of this because I really, really like it. But here is a handicap, which is today's talk is about. What do you mean this steady population? Who forced these people to keep playing? In any game, some things change. And in my model, what will change is people will come and go. They will sometimes vanish. And our main theorem wants to do that. This corollary applies even if I take this last line off of here. So that's the main thing that we want to do. So what I want to do today is convince you that, that I can take this stability assumption out. So I take a game that's repeated but I'm going to make the player population change. And what's my current model of player population changes is a mix between worst case and some amount of randomness. If I worst case change the player population from step 1 to step 2, like, well, that was a different game. So I don't want to do that. But if I make a sort of Bayesian randomness replacement assumption, then the hosting is very steady, and they don't have to learn so much. So what we're doing is halfway between the two. And here is what we're doing. Every step is every player with some fixed probability P, the guy will vanish. And the replacement is an arbitrary worst case other guy. Now, what does this do? First of all, and I'm going to play with how high I can push that probability and still have the theorem. So my main sort of game or whatever, that's the wrong word here. Main thing I'm playing is how high can I make this probability P be and still make a positive statement. Okay, so if P is really, really big, as in like 1, then that was the case, everyone vanished and whole new guys showed up. If I make P virtually 0, then kind of no one ever vanishes. And I want to try to play with what P's can I make reasonable statements for. This is the individual probability. Remember, we have n players. So in expectation, n times P players will vanish. I would like to make P sort of constant. That's my goal. And we're not quite up there. But we can basically will make P roughly 1 in log n. So a very large fraction of the population will get replaced every step.
Every player only plays for 1 over P steps until they
in expectation.
Right? So shouldn't the regret be at most, like don't you then have a regret of at least square root of that?
Oh, definitely, definitely. I'm going to, yeah.
Constant, then you get like constant regret.
So if I pushed it all the way, you're right. All constants are a little too high. I can't go that high because then they're going to have 1 in root P, 1 over root P regret for sure. And worse than that, because they're playing in this changing environment. Okay, so this is the kind of, I didn't invent a new word, and I'm not a big fan of new words. So I adopted the stall price of energy to also mean this. Maybe it should have been this. So this is the cost of a game where I changed the notation to have the player types. Because of my simple model, we always have n players, and n isn't changing. This is just because the math is easier that way. So one guy vanishes, another guy shows up. But I guess 2 examples just to sort of get you the sense of what's going on here. 1 in auction and one in traffic routing. So this is a simple network. Here is a guy that we're going to watch. Maybe he's around for these steps. Maybe when he showed up, this was the case. There are tons and tons of packets going on the upper route, and so he's going to choose the lower route because that's good for him. He'll learn that. But as things happen, in the middle of his still alive, those guys all vanish for whatever reason and replaced with these guys, and then he's going to have to change his strategy. So what this example tried to illustrate, that you're going to have to adopt because the replacement is worst case. So I could strategically, even though I'm randomly deleting people, make it one kind of bad people show up in the worst case. And if you're not adapting to it, you're going to be hosed. This happens in auctions just as much. Here's a guy that sort of thinking whether, say, unit demand kind of buyer. He likes either the orange or the red, whatever balls there are. When he shows up, all these other guys are all buying that upper ball in this right congestion, and it's very high price, but the yellow or whatever that color is kind of cheap. He buys that, but it turns out after a while those guys vanish and replaced by these guys, he has to switch. So whatever context you're in, the game matters. And if the population congests on one side, you're going to have to go over to the other side. So you have to learn. You have to adopt.
Wait, but you compare yourself to the best fixed action, which means that you compare yourself to something.
Okay.
Which is very
So Christian is asking a good point, connecting the 2 things I've said so far, which actually don't connect. Connecting yourself with the fixed strategy with hindsight is a really weak benchmark. You can't get anywhere on that one. So I'm going to have to do better than this. Fixed strategy with benchmark in either of these cases is horrendous because half the time you're doing something really bad. That's bad. Half the time doing bad things, that's bad. So fixed strategy with hindsight is not strong enough. Yeah.
I'm sorry, you're just hoping to get a price of anarchy result at the end of the day.
Yes.
So the fixed strategy in hindsight is really weak and therefore easy to satisfy, but it gives you the price of anarchy result you want at the end of the day, then who cares?
No, true. Good point. Good point. I don't think it does, but I guess I don't.
No, essentially proves the theorem, but it's not that meaningful because
No, it will be.
Anarchy result would be a price of anarchy result regardless of any tools used.
Okay, so what Jason is asking, my goal wasn't to have people learn, but instead my goal was to have a price of anarchy result. It's conceivable. I don't believe it's true, but I certainly don't have a counterexample on my slides to prove to you that you can't do that. You won't get a price if you don't. If they're doing this weak learning, that's weak, and they won't be able to get the price of anarchy result.
It's also
this assumption is too weak, right?
It's too weak.
It's the other way around. If you're assuming that if regret bounds are not very meaningful, that makes the result harder to prove.
Yeah, true. It would be harder to prove, and at the moment, I don't have a proof.
About the strategy.
So what Jason proposes, I guess, could be true. I don't believe it's true. I do not have a counterexample. It definitely would be harder than my theorem. What am I going to do is assume that people are a little more clever than this. And I will tell you in a second what format of cleverness am I planning to assume. Yeah.
Are you going to say formally what is the game here and what does it mean to replace a player, or should I just think of these examples? Will this work for any game where you just delete a row from the matrix?
Good question, and let me actually, I will say something a bit more formal than what I did so far, and can we come back to it right at that slide of what do I mean? And I think you probably best off thinking of these two kinds of examples where it's easy to understand. But as a general game, let me come back to this question. Okay, so I need this last line. I claim I need it. I guess I should have a counterexample that the learners need to adopt. It's also natural to adopt. If you're one of these players, it just feels that like you need to do this. Like otherwise, you're not playing very reasonably. So what do I mean by adaptive learning? So I guess the good news is, as you guys maybe all of you know, among other reasons, because Sean Kokada was here for a long time, there's a large community of people thinking about how to prove learning bonds and what kind of learning bonds one can prove. And I guess the version of the learning bond that I would really I like thinking of as a form of recency bias. That is, if the population is changing, if, back 10 years ago, you guys always used to have the colloquium back in this other room. I accidentally showed up in that room first. That's why I remember this. I need to learn that now you don't. And if I give another colloquium tomorrow, I should be smart enough to come here this time because I have recency bias. I experienced that, yes, in the past it was over there, but nowadays it's in this room. So learners should have English, intuitively speaking, recency bias. Recent experience should matter to them more. And in the model, this makes sense because people are vanishing with small probabilities. So things that happened a million steps ago, a lot of those people are gone. But things that happened yesterday, now that's pretty relevant. Very few people left. So recency bias makes sense. A format of learning that the learning community likes, and it's a very nice extension in the current version, both in the algorithm itself and in the regret they do, is the following form of recency bias. If some fixed strategy, if a strategy X, is good for a pretty long period, a period from maybe calling Ta1 to Ta2, that's a long, think of it as a long period, then you should wake up to this and during that period, play it. If the period is short, I don't care. So I said that your regret should be little low of the period length. When a period is, and I really mean as a period grows, as a function of the length of the period. So in particular, my favorite, I think all of our favorite algorithm is the Luo-Shapiro algorithm, which is a very nice and very simple adaptation of the classical hedge algorithm. But there are earlier algorithms here. The history goes back to a 03 learner paper. And Blum and Mansour has a more complicated algorithm achieving the same regret rate. So it's still the case that multiple algorithms can achieve this. That is learning rate or error rate or regret rate proportional to the root of the error, root of the length of the period. So now I don't have a fixed strategy over the whole period. I would like you to do well the fixed strategy against long enough periods. And what I mean here is your error is supposed to grow proportionally to the root of the length of the period. Again, and again, this is doable, and the algorithms are very natural. And then there are multiple algorithms out there that achieve this band, which are the greens here. In fact, the learner paper from O3 is offering an even more sophisticated version of what you should not regret. But this simple one is natural for us. And what they really do is I think, fair described as a form of recency bias. So what the algorithms do to get no regret is remember how much regret they have and trying to act on this. That is, if you regret something, then do it. Maybe that's a good thing to do. And what these algorithms do is every now and then wipe out the history. Just forget what you had so far. Start again. That's a form of recency bias.
You ask for, and it seems to imply recency bias, but that's not sort of clear to me that the definition implies.
No. I mean, recency bias seems natural, and the algorithms that achieve this do seem to have this property. But for example, I didn't formally define what I mean by recency bias. And if I were to define it, I would more go for the econ style definition from what these guys do. But if you want this sort of a band, which is this top line again with the big little o is what I really want, and you think of your last period, last 100 steps, last 1,000 steps, you do need to have some sort of recency bias. You should do okay on the last 1,000 steps, even if your previous history is 1,000,000 steps is telling you something else, because that doesn't matter now. You should react to the last 10. And so,
Ava?
Yeah.
What's the relationship between this and like the giant literature, like that Drew Fudenberg, for example, is part of on, adaptation of like learning rates in like evolution and things like this? I mean, there's like a big literature on like the evolution of the rate of mutation in order to, deal with environments that are changing. And it's all trying to address problems like this.
So honestly, I should check. I certainly was aware of a dual literature on learning, on the classical learning without this recency bias version, that there's a CS econ dual literature with similar bands.
But this is sort of like evolution in economics.
But I guess this particular, and then also the learner paper is an econ publication. Like it's an econ venue. I forgot which journal it was published in. But the rest of them are CS papers, and I guess I wasn't aware that this particular form of regret against a small interval. I wasn't aware of any follow-up of this learner paper, or I should check. Sorry, my mistake. I should know about this. So like I said last time, I guess I'm again using this as a behavioral model and not as an algorithm. I'm not telling you how to do it. I'm telling you that these guys know algorithms how to do it. Maybe many more guys know algorithms how to do it. There is a recent Fudenberg paper that I do know that is using the more econ-flavored format of recency bias, claiming similar bands, which is very recent. So at least I know some piece of this literature. This has a better convergence band, but the error band here is better. But anyway, so again, I'm using this as a behavioral model. That is, I'm assuming that whichever method they use, whether they like the Fudenberg paper, whether they like Blum and Mansour or Lou Shapira, they're doing something that achieves this regret. And the main thing we're proving, and I'm going to try to at least give you a hint of how or give you an idea of how we prove it, is that the following basic flavored theorem, that we try to prove results on the price of energy in this changing environment with a probability that's roughly proportional to the log of the population, so very high turnover. And these are the two main points I want to make. I'm doing worst case replacements of people. So I believe that causes it to be really necessary for them to do adaptive learning. But I guess Jason wants to contradict, like prove to me that I'm wrong. But at the same time, I'm doing a slow replacement process. That is, every player independently vanishes with some probability, roughly 1 in log n. That is, the fact that they all vanish all of a sudden and some other guys show up is incredibly unlikely. And in this case, I'm going to do real badly, and that's OK, because that's an unlikely event. So I'm using this smooth game framework that was suggested by Tim Ravgarden, who basically suggested this framework to unite or unify a whole bunch of price of energy proofs. And because I'm running out of time here, I'm going to maybe do a little bit less with this than I originally intended. And I'm going to instead switch to the auction version, in which maybe this is a little easier to understand. So here is a version of a smoothness proof. And because I skipped through the smoothness defining slides, I didn't define what smoothness was. But the thing that's happening here will be smoothness. Here's an auction. The setup here is that unit demand buyers, they would like one of those balloons and might have preferences between the colors. Okay? And they have different values. If you think of the optimal solution, the optimal is a matching problem. Every buyer is assigned to an item, or most of them. Say that buyer is assigned to that item. That's the optimal solution. One thing they can do, this is the special strategy or action that I'm going to have them think about, is to ignore all the other items, because magically they now know which one is the optimum, which one they should get in optimum. And in this, just bid on that item and bid half the value on the item. This is, say, a first price auction. They bid a shaded value of the value on that item. This is something they could do. I don't know how on earth they would know to do this, but they could do it. And if they do this, we get this very nice inequality, which turns out to be super helpful. And this is maybe worth reading off. It says that if they play this special bid, half the value on that item, then whatever everyone else did, doesn't matter, they either get half the value. That's because they bid half the price. If they win the item, then half the value is home. Or the price was high. If the price was high, which I will claim is a good thing because auctioneer made a lot of money, the price was high. So either they get half the value or the price was high. And in particular, this inequality holds. So they can, there's a special action. Again, there's no way for them to know, but there is one. That if they did that, there's some sort of guarantee. And the guarantee basically says, I can get a good fraction of my optimum value, that's the first half, or the price is high. And high is, there's no multiplier here, that's why it's 1. If I do this and just add it up over all the players and use the standard and Nash equilibrium, you don't have regret against this particular action, you're home. That is, and I maybe did that in this slide. I said, OK, so if S is a Nash equilibrium, then you don't have any regret against some other action. So in particular, don't have regret against this particular action. This action has an inequality, which we can use from there. And using that property, we get that the utility plus the price is at least, rearranging this, moving this over to the other side, half the value, which is half the optimum. It's a very simple inequality, basically just riding on the thing I squared here. That is, if this kind of property holds, then you can, you're not regretting that particular action. That gives you a welfare guarantee. And what's nice here, and that's again in blue, they don't have to know what the magic action was, because I assume they're learning. They're not regretting anything. This is the action I'm using in the proof. They're not regretting other actions either. But this is the one that they should not be regretting. So this is a classical smoothness proof. And that's the kind of proof I'm going to use. Now, what do I want to do in my remaining 1 minute? What do I want to do to combine this proof with this dynamic population? So we have a lot of pieces that I really want to put together in one last way of how to combine this. So what I would wish to have is this inequality. I would wish to have the property that these players, as they're playing all kinds of things, and they have some type, they're not regretting whatever the optimum is. But bad news every time, or at least on the average. The bad news in my life is that this optimum, this special action, which remember dependent on the optimum, is a very changing action. Every time something else happens, the optimum changes all the time. So for example, with the last demonstration, here is, again, a unit demand auction case. These people are getting the optimal item, but one guy vanishes. What happens? The optimum dynamic totally changes. Everyone should get something else now because the one guy changed, and as a chain reaction, everyone changes in the optimum. So there is one piece I'm missing, and this is the last piece I want to tell you about, that I want to do this. I just don't want to do it with the real optimum. I want to play this game, and this is sort of the high-level theorem, and now I can come back to your question of what I mean by a game. So if I have a game that satisfies the rough garden smoothness property, that it's in the class of games on which we have a smoothness space price of energy band. And that's a pretty restrictive game. So like, I can do it with replacing rows, but they're not going to satisfy that property. So I think you're better off thinking of examples. And second point, the welfare optimization problem, the optimum solution of which this magic action came from, has a stable, close to optimal solution. Has a solution which is with the property that the people's strategies or people's actions don't change much. It's very, very steady as I change people. Unlike the matching, where it was super non-steady. Something very steady. Then you have a price of energy band. Okay, and why? Because what they needed to learn here, going back in this slide, just had to learn not to regret the optimum. If I can plug in an optimum here that's very stable, they can do that. They can learn steady things. They can't learn very changing things. So I need a very stable optimal solution in order to do this. And the one piece that that now you're supposed to imagine, and that's really sort of orthogonal to virtually everything I told you so far, then I have to claim that in many games, maybe in almost all games I could think of, there we can actually get such a stable solution.
So
and there's some assumption.
Algorithm, you don't even care that it's efficient, right? You just want
approximately efficient.
It doesn't need to be efficient, right? The running time.
Oh, good point. Good point. This is not an algorithmic statement. It's an existence statement. I don't need an algorithm that computes this. This is inside the proof. Or if you want, and this is something that I'm philosophically happy to discuss, if you had an algorithm and you want to help these people, you can make suggestions for them of what they should bid if you had an algorithm. And then they should only not regret your suggestion. They don't have to run such a sophisticated learning algorithm.
Yes. This condition looks at least superficially similar to differential privacy type of condition.
Yes. How did you guess that? So because you guys were a great audience and asked many good questions, there is a flight I just passed through, which I definitely don't have time for. In the unit demand auction case, one can actually show you that one can do this stable solution without any machinery. Like there's a pretty simple greedy algorithm based. I can just do it directly. I can give you a pretty stable solution. No assumptions, no nothing. It just basically, the idea is to don't use the optimum, use the greedy algorithm. But very much more generally, I want to end with the connection that Boaz just made. There is another notion out there with a large literature that we can cash in on how to get stable solutions to problems, and that's because of privacy causes. If you're playing a game, and if you're worried that because you guys see what's happening in the game, my properties or my desires will leak to all of you, we might want a solution with the property that you guys' solution is not very sensitive to whatever I told the mechanism designer. That's called differential privacy. And how do you achieve this? That your solution is not sensitive to my input. This is precisely what I wanted to. Your solution should not even be sensitive to whether I'm there or not. That's what I wanted. And that's precisely what differential privacy does. So using the differential privacy machinery, there are two classes of games to be proving positive things, and this has the details, but I'm not sure it's definitely not worth reading. We can do statements like this on general congestion games. because there are nice different papers on how to get the optimal solution that way, differentially privately, and literature largely championed by Aaron Ross and many other people working with him. And similarly, also Aaron Ross and co-authors, large combinatorial markets with growth substitutes. Here he's making a largeness assumption. He's making the assumption that there are enough items around to cause this to happen. Okay, and I'm going to stop here. And thank you very much for your attention.
Questions?
Yeah.
Do you know any negative examples of welfare maximization problems that don't admit an approximate solution that varies very little when you change one player?
Good question. No, I don't. There are two sort of big classes of games here. In this category, I don't believe it's possible, but I might be wrong. The Aaron company paper with growth substitutes does make a very large game assumption, and they need it in their proofs. But our version, which I admit is unit demand only, doesn't need any assumption. So I'm kind of thinking we just need to bridge the gap here. We're just doing, like, there is an algorithmic issue. Like this is a particular tool that we can't use because this uses the large game assumption, and this is a simpler setup that we need to deal with. I think that's bridgeable. In the congestion game version, I'm less sure, but I don't have a good example. Yeah.
There's a literature on informational smallness, especially a paper by Al-Najjar and Smordinsky, which takes these complete information settings that you're considering, but then puts in some incomplete information into them, and then shows that under some general set of conditions, no individual can make much of a difference to many players' allocations in some broad set of cases.
Oh, so
that might be, that's not exactly your setting, but yours says complete information, with some perturbed version of it.
Sure. Sure. And it's not like, certainly, I should, thank you. That's a great suggestion. It's not clear it's so different because for what, like one nice thing about games that you don't need the shared prior assumption for the classical Bayesian games, they're just learning. It doesn't matter what they know. But in particular, it's reasonable to assume that they don't actually know all the players they're playing against. Like there's some random variation on players and they don't know really what's going on. So there is some informational issue here that we're not explicitly exposing because we're making the learning assumption, which makes it go away. But they're certainly there in the background. Yeah.
Okay, let's thank Eva.
Thank you very much.